Thank you very much. Yes, my name is Andrew Emmons. I'm the CTO of UITV in Ottawa, Canada, and I'm joined by Erik Uggeldahl, who is our developer relations manager. And we're here today because React Native has about 56,000 lines of C++ code, and sounds like it's growing. And for the common developer, that's probably not consequential, but for us, we're here to tell the story about how it's changed our company over the last 2 years. And we're in the business of the media entertainment streaming apps. So we help companies create beautiful looking streaming apps for the media entertainment businesses. And we help them go across as many platforms as possible. And in that industry, getting on platforms is key. It's not just getting on a mobile, but it's getting on gaming consoles and smart TVs and set-top boxes. And it's really important for them to be on almost as many screens as possible. And so we help them do that by having what's a C++ engine. And so what we have is a C++ engine that uses things like shader APIs and GPU APIs that draw all the pixels that you see on the screen. And by doing that, it lets our customers have sort of a unified UI across any platform that they're on, and it helps them have a common code base to render and implement that UI. This is not a new thing, for sure. The problem of this code fragmentation and having separate code bases for all these platforms it has been solved many different ways and for different industries. We took a page out of the gaming industry where there are C++ engines and GPU shaders that help them render the graphics on any platform. And also, of course, Netflix is known to have a C++ renderer to help them get on a lot of platforms with the common UI. So we have this UI engine, we've had it for a while, and we've worked with a lot of major brands in the world around the streaming video industry. We've used this successfully to create apps that go across platform, relatively performant, very performant, and also a very good UI. And the problem that we started running into a roadblock a few years ago, and it was the problem where the issue that the very thing that gave us that ability to go cross-platform and to have a unified framework was also causing problems in that these apps themselves that were built using C++. So I'm sure all of you in the crowd have written apps before, but I'd be curious to know how many would have written C++ apps. It's not a common language that you use. And so what we were running into issues where our customers really couldn't find developers that would want to write C++ apps. So we started looking at JavaScript. This is around 2016. We started looking at perhaps there's a way to have JavaScript APIs that sit on top of our C++. And of course, those are all proprietary. It didn't really work out well. It just looked like C++ APIs in JavaScript. And so we started looking at React Native. And we really liked what we saw with the JavaScript APIs available on the React Native framework. And we figured, well, what if we could add, for React Native, another platform? So we knew, of course, that there was, at the time, like the React Native for Android. We knew there was a React Native for iOS. And we said, well, what if we were to become a React Native for our UI engine? And so we would be able to take our UI engine and have that across all the platforms. We'd have the best of both worlds. We'd have the ability to go as many platforms as we need to, but we'd also have a great usable API that developers would love with an ecosystem to support. But we didn't know how to do that. React Native was new to us. We hadn't looked down into those red boxes to figure out how that binding was done. So the next stage we did was we took a look at the React Native code base to see how the native implementations were actually being created. And as was discussed in the last meeting, one of the key parts there is the bridge. The CXX React is really the folder in there that implements the bridge. There's a lot of great classes in C++ in there that help implement the message queue and the JavaScript executors. And at the time, we were very excited to see that. That looked like really the heart and core of the React Native system, and we're excited to see that that was done in a C++ way. The next thing that we were worried about was layout. Our engine had its own layout system based on anchors, kind of like Unity. And we had a lot of respect for the Flex system, but I didn't want to spend the time implementing a Flex layout engine. So as we dug deeper, we were really excited to see that there was something called CSS layout, eventually turned into Yoga, which is a great name for a Flex layout engine. I think it was a matter of a couple of days that we had the Flex engine interacting with our system to be able to give the right measurements and positions of items. So that was a great thing as well. Another worry of mine was related to the differences with C++ and JavaScript, really around the dynamic typing. And so I was happy to see that Folly had this thing called Folly Dynamic, which was this dynamic data type, but implemented in C++. And that was a big worry gone as well, because that's a big part of any kind of JavaScript, C++ integration, is how to get this dynamic data type working and serialized and all those good things. The next piece of the code base that we saw, not really part of React Native in particular, but a big part of our strategy, is that when you go into these platforms, of course, you're going to need a JavaScript interpreter. We knew that JavaScript interpreters, they're all implemented in C++, from of course, JavaScript Core to Chakra to V8, even the new Hermes, thankfully, is C++. So that was a big part of it, because as you go into these different platforms, the JavaScript interpreter, it might be already existing on the platform, or it might be the current one is too big and it has to have a smaller footprint. So it's really important to be able to have consistency there and choices for the JavaScript interpreter. So this was a few years back, and it was great to see. And it's even greater to see that Facebook has continued to adopt this C++ strategy. As we just heard, with JSX and native modules and the renderer, a lot of that code we could see getting put into GitHub looks to be C++, which we're very excited about for the future. And so back again in 2016, when we saw all this, we were super excited, because it told us that we could have another C++ platform. We could be like a third platform, React Native, and it wouldn't be just shoehorned in as kind of a hack. We could sit there and work with the systems that are already in place and continue to evolve that over the years. And so I remember showing, I think Erik was the first person that UI showed this to. This is done in 2016, late 2016. Some programmer art there, I guess, shows the movies popular at the time. But it's running on OS X. It was using the Hello World app that was from React Native at the time. I hacked together a few other things to just demonstrate a list view and an image and text. But this is rendering with our C++ engine, working with all of those different components in React Native. And I remember, I think Erik and I fist bumped at the time and caused a bit of commotion in our area or whatever, but we thought we were onto something pretty special. And we knew that we could bring a C++ engine across all the platforms that we wanted to using React Native.
So let's talk about some of the properties of C++ that make it appropriate for this kind of work. And I'll also talk about some of the nuances of each platform and the architectures that this kind of naturally lends itself to. Before we do that, though, and Andrew kind of hinted at this, I think we should address the elephant in the room. C++ has this reputation in the industry, right? It's kind of due to this accumulation of features over the years, and it really does prioritize flexibility over ease of use. And that's given it this rep of being difficult, if not even impossible, to truly master. Usually, a company will look at it, take it, and then choose some subset of the language that they're going to adopt and stick with, and everything else is just verboten. So this general perception is the reason why we use the words dark power in the title of our speech, but I think with the right kind of attitude here, we can shed some light on it and show that there is hope in taming this beast. So broadly speaking, it is considered a systems language. And this is as opposed to other languages, which are sometimes referred to as applications languages, such as JavaScript. This means that it does concern itself with the hardware it's running on, the cost of its abstractions, and the management of memory. And because of these constraints, it does lend itself to being statically typed, ahead of time compiled, and it lacks a built-in garbage collector. And there are a host of ways that you can compare two languages, but this is just a few of them. Other languages in this category include its predecessor, C. You have D, and a personal favorite of mine, Rust. They all play in the same space, so feasibly, any of them could have been chosen for this role, but C++ has a good deal of momentum behind it, and that momentum can be difficult to escape sometimes. A lot of this momentum does come, in fact, from the games industry, which did inspire our approach. And so at UITV, we also happen to hire a ton of game developers, and they're kind of experts when it comes to cross-platform development on restricted and varied hardware. For them, that's just a normal Tuesday of working in those conditions. For decades, they have had this concept of a game engine, which abstracts the platform that you're working on for functions that are critical, like networking, file storage, input, and most importantly, rendering. The engine does attempt to provide these abstractions as well, while also paying as little as possible for them. That's one of the key tenets. And so what this has led to is this pervasive culture of performance throughout the games industry. And we all kind of know this figure, right? That 60 frames per second is seen as this ideal rendering rate. And this means that you're really operating with 1/60th of a second, or said equivalently, you have 16 milliseconds to do all of your work, which includes user update, or user input, update, and then a render of all of those results. And if any part of this process, that whole chain, takes longer than 16 milliseconds, this is called a frame drop, or in the apps industry, we sometimes hear it called jank. And in general, it's quite frowned upon, as you can imagine. And engines, therefore, are in this constant state of improvement and research, where we're looking at optimizations and trade-offs that might even save just fractions of a millisecond. And this has resulted in some really cool modern modes of thinking, like data-oriented design, as exposed by people like Mike Acton. He originally worked at Insomniac Games, now he's at Unity, and he has this talk here, Data-Oriented Design in C++. If you're at all interested in performance, this is one of the most eye-opening and inspiring talks I've ever seen, and every year I kind of go back and I get a little bit more from it. So, with all of this in mind, how would you go about building a game engine? We have one, obviously. It's called the UI engine, very creative. But broadly, the steps involved are the same across all of them. And this is true as well of the React Native C++ layer, which is a non-game engine as well. They're kind of all operating on the same constraints. And at the lowest layer, you have the platforms themselves. And so what we're showing here are the ones that we're personally concerned about, but you can pick any subset you want. And I'm about to show you a lot of information that, please don't memorize it, but I just want to give you the impression that there is a lot of variation between these platforms, and there's a lot of considerations that you have to make. So firstly, they each have a way of authoring, and this is kind of the blessed language that the parent company has chosen for an app developer to use. And then also, a lot of them, pretty much all of them, will expose what is called a native development kit, sometimes an NDK, and that has some way of compiling C++. One exception to this is Roku, which Andrew's going to cover later in this talk. And that one certainly required some creativity. But these two layers that you're seeing here have some mechanism to bridge and bind between them with varying degrees of complexity depending on the platform. Then you have the physical hardware that we're running on. And that has a CPU which has a dedicated instruction set architecture. And to execute our C++ on that, you're also going to need some sort of compiler that's capable of generating machine code that is particular to that CPU. The compiler is generally provided as part of the SDK, and any cross-platform technology, ours included, as it matures, will naturally start to make advantage more and more of the features in that compiler, such as specific optimization flags, or attempting to leverage SIMD solutions such as Intel AVX or ARM Neon. And then there's the rendering method, which connects you to the system's graphics hardware. This uses a graphics API, which is typically OpenGL, but not always. These APIs include a separate language for running what we call shaders, but they're really just small repetitive instructions that are run on the GPU. It's a different language entirely. For games, this is not optional, but for apps, we kind of have a choice in front of us. And you could choose to bind to the native UI toolkit, and this is the default approach by React Native. Many people have strong feelings about this, right? This is the right way, this is the wrong way. I'm not really here to get into that, and I think it's a topic deserving of a talk on its own, so I'm just going to gloss over it, but in general, you're kind of trading strict adherence to a platform's look and feel, and in return, you're getting uniformity of the graphics across all of them. And one thing to bear in mind, too, is that of all the platforms, iOS, Android, and UWP really do have the strongest guidance. And outside of that, it really starts to drop off. At UI in particular, we're also pretty concerned about video playback because we primarily deal with media companies. And so this opens another can of worms that aren't as relevant to this talk, but I thought it would be interesting to give a glimpse anyhow. So you've got each platform having its own video player with their differing APIs, and then these players accept different playback formats, and then those playback formats have their own copy protection. So it just creates this really big matrix that grows and grows and grows. So now that we've covered the landscape of underlying platforms, we can begin to form some really nice abstractions. First, let's start with rendering. Oftentimes, this is called a rendering pipeline, which marshals all the data required for the graphics API in a unified way. And one of the most common ways of doing this is to take all your renderable objects and represent them in a tree structure, sometimes called a scene tree, other times called a scene graph, doesn't really matter. And what I'm going to show you here is an example of this from an open source game engine. It's really up and coming if you're interested at all in game development, called Godot. And each node has information on position, opacity, focus state, and so forth. So all that information in each node. And every frame, the engine will descend the tree and look for input, update, and render operations. We can then group these nodes into more meaningful UI components. And we call them views. Most people would call them widgets. And this allows us to add behavior for buttons, images, lists, and so forth. Other important areas include text rendering, focus management, layout, animations. And these all have their own fascinating complexity that we're not going to get into. So outside the scene tree, you have non-visual systems, and we can aggregate these using platform bridges, and you can unify the raw APIs coming from the underlying system. From there, you can massage them into system abstractions, giving you events, input, asset decoding, memory, threading, networking, and authentication, among others. If you were to create all of this, you would have a fully functioning C++ engine that could create applications on all platforms. Qt would be another example of having this same kind of architecture. As Andrew mentioned, when we entered the media space back around 2014, this was also the state of our engine. However, like we're saying, C++ not the ideal language for writing apps in, so you might reasonably start hunting for an alternative, which we did, and as you can guess, we settled on React Native, and this led to the exercise of binding both the virtual tree and the JavaScript bridges to our existing abstractions. We launched the React Native interface with our 5.0 engine back in August 2018, and since then we've just been improving it with monthly releases. We also did decide to take this one step further and take another cue from the games industry. In their studios, artists are given standard 2D and 3D software that has plugins that export directly into the engine to give you characters and environments. This is often referred to as a workflow, and it means that artists are directly involved in the creation and production process. We took a gamble that this would apply equally as well in the apps industry, and we created a plugin into Adobe After Effects, which would allow designers to fully realize their layout, motion, font, and branding goals directly in a visual tool. This is similar to Airbnb's Lottie, if you're familiar with it, though the intent is to create entire screens using it if so desired. It is optional with React Native, by the way. We use, as an interesting tidbit, Google's protocol buffer as the serialization and compression format to go between the two. So, of course, all of this architecture would be for naught if it was not running at a decent speed, and if it didn't consume a reasonable amount of resources on physical devices. We know that 60 frames per second is kind of the ideal metric, but how do we achieve it? So it's really no different from any other optimization process in computer science. Firstly, we need to identify the bottleneck. That could come in a number of places, and it's based on the various resources that we work with. The first is the CPU, and specifically the main thread, which can quickly become quite saturated. Here we could look at exchanging an expensive algorithm for one that's more efficient. We might look at threading, if that's an option. And if it's not, we could look at taking a long-running operation and break it over the course of several frames. If we consume too much memory, we might be forced into the virtual pages of the system, which are much slower, or in some cases, the operating system might warn us before unceremoniously just terminating the app. So to solve this, we can look at techniques like lazy loading, where pages have their elements loading deferred until a time when they're absolutely necessary, or at a point when we can unload older chunks of memory and that they're no longer necessary. If the problem is due to having too many repetitive allocations, we can start to look at another technique called memory pooling, also sometimes called a memory arena. And this is great for instance, list items, which have a bunch of the same template, but only the data differing between them. And then we've also got networking. That's another bottleneck. If we don't aggressively cache our data, we can find ourselves refetching the same information over and over again, including for simple things like just going back. That data is not necessarily stale, and we should be looking at keeping it around as long as possible. We can also do things like fetching in the background and having a slightly longer loading time up front if it means that we have a perfectly smooth experience from then on. Another technique from the games industry. So that list wasn't exhaustive, but when building a system, we need to be conscious of the trade-offs we're making. The benefit of working with a system-level language like C++ is that these options are all exposed to us. We choose exactly what allocation scheme we want. We choose exactly what image decoding algorithm we want. We choose when and how to cache all of our network data. As mentioned, we can even investigate the low-level techniques like SIMD that perform calculations in a way that are at least friendly to the compiler that's performing the end optimizations for us. But none of these optimizations truly matter if they aren't the critical bottleneck. And that's why it's so important to use every tool at our disposal to profile, measure, and identify the true source of slowdown. Often, it can be unintuitive, and if you rely on your intuition alone, you may find yourself spending a great deal of time optimizing sections that simply don't matter. Thankfully, C++ has a wealth of veteran tools available to get an accurate measure. In one instance, we identified a well-meaning artist had put a background image, a very large one at retina size, and it was simply just a gradient with transparent overlaid ovals. And when fully decompressed on the GPU, it was a whopping 20 megabytes. We reduced this to a 1-pixel wide gradient and stretched it out, relying on the GPU's ability to perform basically free bilinear interpolation, and then just added the instanced oval back on top, and this reduced it to a simple 100 kilobytes. And that was only identified because we had measured it, and it stuck out like a sore thumb that there's this one massive image in there. And one other, and I'm repeating myself here, and I'm sure we're going to hear more about this, but it's an important factor to consider the JavaScript engine that you use as well. They're almost exclusively written in C++, and by interfacing with them natively, we're able to tune them to the desired specification. So as many of you know, Facebook released Hermes, and it has a significantly different set of trade-offs over JavaScript core. The landscape roughly looks like this. You've got JavaScript core coming from Apple on WebKit. You've got V8 by Google on Chrome. You've got Traka by Microsoft on Edge. You've got SpiderMonkey by Mozilla on Firefox. And now you have Hermes, now you have Duct Tape, and you've got QuickJS. So there's a whole landscape out there. And the point is that they all have trade-offs, right? Such as a JIT capability, warm-up time, install size, ES6 compatibility, and platform restrictions. While it's beyond the scope of this talk, and I'm sure we'll get more coverage today, I would recommend reading on the decisions that Facebook made regarding Hermes and why those trade-offs are, and why we're willing to make them on non-desktop platforms, such as not having a 4-stage JIT in the background, because it's just not as relevant for mobile and embedded devices.
As Erik mentioned, so NDK is a good way to get C++ access on platforms, but some platforms don't let you do that. And Roku in North America is quite a popular platform, and they have something called BrightScript, and they say if you want to write an application, it has to be in BrightScript. And we needed to bring and wanted to bring our cross-platform React Native solution to the Roku, which is BrightScript. How can you possibly do that? So we had this crazy idea, in my opinion. We had this problem also in the C++ application as well. But we are cross-platform. We can build on Linux. What if we had either a C++ or a React Native application running on Linux somewhere in the cloud? That wouldn't really help anybody. But what if we then, instead of when we go to take that scene graph that Erik mentioned, and we render that to the GPU, what if we were to take that, bottle that up, and send that data model over to the Roku on a thin client system? And that thin client system on the Roku would just be BrightScript, it would be kind of dumb, and it would take this data model, and this data model wouldn't be pixels, it wouldn't be like streaming pixels like you see in some of the game streaming. It would be, here's my button, this is where it is, here's the animation for it, this is my list, it has 5 items, here's the URL for them, so it'd be at a higher level model. And the device itself would render all the components, and so you wouldn't have the latency of as the user moves through it, of having to go back to the server. It would reduce that. And so what we did is that we did that very thing. You can have a React Native app running on the cloud, hooking up to this thin client. The thin client then takes the scene graph and renders that, and you have a React Native-based app on BrightScript. I'll show a 10-second video. It's pretty short, but I'd like to show this here. How do I get it to play?
Over there. Look at the TV on there. That's where your mouse is.
Right there? Oh, okay.
Yeah,
Right, there we go.
One more.
So that is running on the Roku device, a React Native-based system running through our cloud server from Redbox in the US. As Erik mentioned also, that we did have this Aftereffects system, and we really wanted to be able to still have those wow moments where, as a developer, it's really difficult to implement some of the animations and systems that designers have. But we also wanted to leverage the power and flexibility of React Native. So what do you do with that? And what we came up with is a system using custom tags. I gotta get focus back to a system using custom JSX tags. So as a developer, you could write your business logic, write your UI, but when it came time to maybe enhancing a screen, you could add custom JSX tags to it. And essentially what we did is we add this concept of a reference, so an image ref and a text ref, and a layout ref. And those items, they had the same APIs as the React Native counterparts, but it let the developer take the presentation and the animations from this Aftereffects tool instead of using the presentation layer that was in the JavaScript JSX. And what that let us do is have these really nice, interesting animations that controlled the UI itself, not just some clip art and stuff, but they're integral to the UI, and have that brought in from an external file. And JSX was the key to us being able to do that.
So to conclude, I think we've covered a lot of ground here, and we hope that at least some of it was useful to you, at least in understanding the architecture that underlies a lot of cross-platform development and concerns that necessitate systems-level thinking. When working with React Native or any other framework, we encourage you to take the time to understand how it's implemented. And in doing so, you will learn to have better sympathy for the hardware it's running on, make wiser choices with your trade-offs, and find fascinating overlaps with neighboring disciplines like we did in game development. C++ kind of is a dark power, but one that, when properly understood, can allow you to maximize your performance and take your code to any platform on this planet. And once you get there, there's a world of opportunity to take your apps to new heights and new territories. All you need to do is look under the hood and take that first scary step. Thank you.